Hello, welcome to the NPTEL course Fundamentals of Composite and Cellular Materials. The topic for today's lecture is Thermal Properties of Foams. In the last several lectures, we discussed about the deformation behavior of foams in detail. We discussed separately about the deformation behavior of honeycombs, open cell foams and closed cell foams, and we discussed about various deformation mechanisms and also deformation modes, especially compression. In the last lecture, we discussed about the deformation behavior of foams at various temperatures. I also discussed about the strain rate dependence, and finally, we discussed about the foam anisotropy. In this last section, we discussed that how the cell shapes they have an influence on the foam behavior, and if the foams are perfectly spherical or cuboid in shape, we learned that the foam properties are identical along all directions. However, if the foams or the cells are not spherical or cuboid, for example, they have a specific aspect ratio, then the properties also differ, and the aspect ratio of the individual cells, they actually control the mechanical properties of the foams. In this lecture, we will cover another very important property of the foams, and that is the thermal property. As we know, the thermal properties of foams are very important, especially because foams are very attractive for thermal insulation applications. We learned when we discussed about the polymer foams that polymer foams have excellent thermal insulation properties. At the same time, we also learned that when we go for high temperature applications, for example, in applications where temperatures more than 1000 degrees Celsius is required, at those cases polymer foams are not attractive and ceramic foams are attractive for those applications. So, in today's lecture, we will learn about different aspects of thermal properties of the foams. We will start with the applications of foams where thermal properties are important, for example, thermal insulation, and then we will learn about some of the more important thermal properties like melting point, thermal expansion coefficient, specific heat, thermal conductivity and thermal shock resistance. We will see that these properties are very important to understand, and the structure and property of the foams are very important to control this behavior. The main keywords to be discussed in this lecture are thermal properties, some properties of fire bricks would be discussed, then melting or softening point, expansion coefficient, specific heat, thermal conductivity, thermal diffusivity and thermal shock resistance. So, as we see in this slide, thermal properties of foams are very important, and if we see the properties and applications of foams, we will see that most of the applications of foams are found in thermal insulation applications. When we learned about the applications of foams at the beginning of this course, we learned that two of the most important applications of foams, one as energy absorber and the other one as thermal insulation properties or thermal insulation materials. The energy absorbing behavior we will see in the next lecture, and in this lecture we will learn about the thermal insulation behavior. Now, we also learned that the foam structure can be classified as either open cell foam or closed cell foam. We also learned that the open cell foams are more important for applications where transport properties are very important. For example, for bioscaffolds application or also for applications like sound absorption material. Whereas, when it comes to thermal properties, the closed cell structure is the most attractive one. And the closed cell foams, they can actually provide a very low thermal conductivity, and that is why they are ideal for thermal insulation materials. Now, the foams or cellular materials, be it a metal, be it a polymer or ceramic, they have very low thermal conductivity, and this low heat flow through the foams are because of many attributes. One thing is that the foams, as we know, they have a low volume fraction of the solid phase. So, as we already learned that most of the properties of the foams are a function of the relative density, which is nothing but the rho star over rho s, and that is why if we actually fabricate the foams for thermal insulation applications, this rho star, that means the relative density should be as low as possible. because as we know that the bulk solids, especially like bulk metals, they have a high conductivity. That means, if we want to fabricate a material with high insulation properties, then we should reduce the amount of the bulk solid in the material, and that actually gives the foams extreme amount of engineering capability, because the fabrication techniques and material design selection can actually reduce the value of rho star, and by doing so we can actually have materials with a very less amount of solid material with low thermal conductivity. Also, the foam cell size also plays a very important role, because the cells, as we will see afterward in today's lecture, the cells typically have up to maximum millimeter and mostly sub-millimeter dimensions, typically in micron level, and these dimensions do not allow sufficient fluid convection, which also reduces the conductivity of the overall foam. And also, because of continuous reflection and absorption, radiation also becomes very less, and also the foams, especially the closed cell foams, because we know that the closed cell foams may have some fluid, mostly a gas within the cells, and also the open cell foams, they have the air filling up the voids between the cells, and these also have a poor conductivity. So, all in all, foams have low thermal conductivity, and these low thermal conductivity of the foams make them very attractive for many applications, like in applications for very advanced applications like oxygen rocket tanks, and also for day to day applications like the coffee cups or the hot disposable cups, and also for frozen food industry or for many other applications where these foams are actually filled between two layers or two layers of wall, and these actually provides insulation to heat removal. Some common applications of foams or for thermal applications are shown over here. The left hand side, or this left hand side image that you see over here, this is a typical application for deep space rockets, where this is actually a foam, kind of a made of a foam, and which is designed actually to provide very high thermal insulation. The second diagram, the second figure that you can see over here, this is very common in countries where there is lot of, there is a very harsh winter, like Siberian countries or European countries. In those places, for the rooms are actually insulated, and these polymer foams, which are part of the construction of the walls, they play a very big role in kind of providing kind of protection from the very harsh winter. And the last one that you see over here, the right hand side, this is a very common example which is used to keep the liquid, or kind of like maintaining ice creams cold, or like keep the food frozen for a long time. These are again applications of the foam structure. Now, as we mentioned, so among the thermal properties of foams, the most important properties are the specific heat, the expansion coefficient, and also the conductivity and the thermal shock resistance. In today's lecture, we will discuss about these individual properties separately. If we discuss about the thermal properties, one of the very common materials where these properties play a very big role is the fire bricks. So, as we know, fire bricks are very common materials for insulation purposes, like also for furnaces, and everywhere we use fire bricks to give protection from like heat loss. And these fire bricks, the good insulation properties actually lead from the very nice structural properties, like as we see over here, fire bricks have a very low density, like 0.3 or even low. And that is the reason that if at such low density, so fire bricks have very less amount of bulk solid, and most of the material is actually made up of air. And that is the reason that because of the low amount of bulk solid, fire bricks they possess low conductivity and high insulation properties. Also, fire bricks, because they are made of ceramics, and as we know, ceramics have high melting point, and they are also very protective at high temperatures, and that also renders fire bricks applicable to high temperatures. Fire bricks also possess low conductivity. So, as we already learned that fire bricks, they have high amount of porosity, and this actually renders the material to low conductivity, and that also makes them very good as insulation material. And also, because fire bricks have high amount of pores, and the pores, they also reduce the Young's modulus of the material, and that is the reason that these fire bricks, they also have very good thermal shock resistance, because you will see afterward the thermal shock resistance of a material is actually a function of the Young's modulus. The higher the Young's modulus, the more is the thermal shock, because you have more thermal stress generation. And also the fire bricks, they have less heat capacity, and this also means that we require a less kind of less, I mean to raise the temperature to certain amount, the fire bricks require less heat, which is also very attractive for furnace applications. Now we discuss about the individual properties or thermal properties of the foams. The most simplest one that comes to our mind is the melting or softening point. Now we earlier discussed about the material properties and their dependence upon porosity. We learned that there are certain properties which do not depend upon the porosity at all, and melting or softening point of the porous materials is one such property. So, melting point or softening point of the porous materials, it not dependent upon the porosity of the material. That means, be it a bulk material, be it less amount of porosity or be it a high amount of porosity, the melting point will always remain the same. Molten aluminum, I mean the bulk aluminum or porous aluminum, they will both melt at the same temperature. So, we can expect that porous ceramics, because ceramics have very high melting point because of their covalent and ionic bonding. So, porous ceramics also have a high melting point, and melting point of polymers are very low, and melting point of metal foams are intermediate between the ceramics and polymer foams. And this again dictates the applications, and that is why the polymer foams, as we know, they are very applicable for low temperature applications where you want to reduce the weight, such as simple applications like packaging or ear plugs or many other applications at room temperature. Polymer foams are very attractive. However, if we go to very high temperatures like thermal insulation, where high temperature is a very important aspect, in those applications polymer foams are not good, and we have to go for metal foams or ceramic foams, especially ceramic foams like porous alumina, porous silicon carbide or their composites, or even applications like ultra high temperature applications like in space applications where porous zirconium diboride or their composites are very attractive because of their very high melting point. Next is the expansion coefficient. So, expansion coefficient, as we know, that as we heat up, as we raise the temperature of any material, it's typically the materials undergo an expansion, and if we reduce the temperature, the materials undergo again a contraction. And again, just like melting point, also the expansion coefficient of the foams is also not dependent upon the amount of porosity, and it is actually considered that the expansion coefficient or the CTE of the foams are actually similar or same to the CTE of the bulk materials. And here again the polymers, they have the highest expansion coefficient, and the ceramics, they have the lowest expansion coefficient among the basic material classes, and this again comes from our initial discussion that because of the bonding, because the ceramics have the strongest bonding, and that is why when we increase the temperature, the ceramics they expand less, while the polymers they expand more. And again this bonding and this expansion coefficient is again very important, because as we keep on heating a material, then there will be, like in case of ceramic foams, there is less amount of deformation than the polymer foams, and the metal foams are intermediate. And this again renders the materials, for example, the ceramic foams, because they have a high expansion coefficient, they are also very much protective against the thermal shock, because we will see afterward the thermal shock is actually a function of the expansion coefficient. The more is the expansion coefficient, because thermal strain is nothing but the thermal strain or epsilon is nothing but alpha times delta T. That means delta T is the temperature difference and alpha is the expansion coefficient. That means the higher for same delta T, the higher the alpha, the more will be the thermal strain, and thermal stress or sigma is nothing but our E times epsilon, where E is the Young's modulus. That means the higher the modulus and the higher the expansion coefficient, the more is the tendency for thermal shock damage. So, ceramics, because they have a low thermal expansion coefficient, so they are very good for thermal shock resistance. We will see it afterward. The next property for foams, which is very attractive for thermal applications, is the specific heat. So, what is specific heat? Specific heat is defined as the energy required to raise the temperature of a unit mass by 1 degree Celsius. So, again we know that the specific heat can be either in constant pressure or constant volume, and again the foam specific heat, I mean unlike melting point or expansion coefficient, it depends upon the amount of porosity, but mostly it depends upon the amount and not the shape of the pores, but mostly on the amount of pores. So, this relation, this rule of mixtures is typically used to actually find out the expansion coefficient of the foams with respect to the expansion the specific heat of the foams with respect to the specific heat of the solid and the fluid materials. So, in this expression here the Cp solid is the specific heat of the bulk solid, and M solid is the specific heat of the mass of the solid in the foam, and the M foam is the total mass of the foam. So, we can see over here that I mean here the influence of the gas phase or the fluid phase, the fluid is mostly a gas in case of the common foams. The influence of the this gas phase is very low, because in general the mass of the fluid that is contained is negligible. So, basically we see over from this relation that because of the so the mass of or the specific heat of the foams is mostly controlled by the specific heat of the solid, which actually constitutes the bulk of the foam. The next and one of the most important property is the thermal conductivity. So, thermal conductivity, as we know, this is actually this actually controls that how the heat actually transfers from one side of the body to the another side if the two sides have different temperatures. For example, as we know that if one side is exposed to a high temperature and the other side is exposed to a low temperature, then how fast the temperatures on both sides or through the material will be equilibrated, that is the thermal conductivity of the material. And again the thermal conductivity of the material is typically follows the Fourier's law, where Q is the amount of heat flowing across the two surfaces at different temperatures, and nabla T is the temperature gradient. So, basically this expression is actually for steady state condition, where the thermal gradient or the profile remains constant over time. But in the more normal cases or more actual practical cases, we have the unsteady state condition, and in those unsteady state condition we have to use this expression over here, where rho is the density and Cp is the specific heat. So, basically this rho Cp dou T over dou T equal to dou x of lambda dou T over dou x, and this lambda is the thermal conductivity. So, if we now simplify this equation by first assuming that lambda is a constant, it is not temperature dependent, then we can take lambda out of this parenthesis, and we can then simply simplify this expression as dou T over dou T equal to A times dou 2T over dou x2, and this A, this is nothing but the lambda over rho Cp, this is the thermal diffusivity of the material. So, this is a very important expression to actually express the thermal conductivity or to relate the thermal conductivity, the thermal diffusivity and the specific heat with the density of the material. Now, the question is, how does the thermal conductivity of a foam or cellular solid depend upon its structure, and what are the factors which control the thermal conductivity of the foams? Typically 4 factors are there which control the thermal conductivity, which is being shown in this slide. That means, if we consider that the lambda star or this term over here is the overall thermal conductivity of the foam, then this has 4 contributions. The first contribution, this lambda S star, actually comes from the solid material contained in the foam. That means, if a foam is made up of copper or aluminum, for example, the contribution of the solid in that foam or the bulk metal or the bulk ceramic or bulk polymer, whatever, of which the foam is made, this contribution is the lambda S star. Then the lambda G star is actually the contribution of the conductivity of the gas contained within the cells. So, as we know that if it's an open cell foam, all the cell faces are open and it is filled up with air, and if it is a closed cell foam, again the cell faces or the individual cells, they are filled up with, especially more commonly a gas, and this gas will also have a conductivity value. So, this term, this conductivity of the gas, actually this provides the second term in this lambda G star. The third term, this lambda C star, is the convection of the fluid or the gas through the cells, and the last term over here, this lambda R star, is because of the radiation through the cell walls and the voids present. So, these individual terms, the lambda A star, lambda G star, lambda C star and lambda R star, this actually in total they actually control the conductivity of the foams or cellular materials. Now, among them the most important contribution actually comes from the lambda S star, because this lambda S, because as we imagine, I mean if it is a foam made up of the solid struts, if it is an open cell foam, or if it is a closed cell foam made up of solid struts and the faces, then the solid of which the foam is made of, this has the highest conductivity, because as we know the gases have very less amount of conductivity. So, gas conductivity of lambda G star, this term has negligible contribution. So, the highest contribution actually comes from the conductivity of the cell walls or the faces material, and this is the lambda A star. So, basically the lambda A star, so the lambda A star along with, I mean if we just use the multiplication sign over here, along with a function of the rho star over rho S and also a shape function. That means, it is also important to consider that shape function, we can use it over here. That means, the overall conductivity of the or the overall contribution of the solid material to the conductivity of the foam has actually three terms. One is the lambda S, that means one is the bulk conductivity of the metal or whatever material of which the cell is made of. Then the relative density, it also plays a very important role. That means, as we can imagine, the higher the relative density, the more will be the bulk solid phase and the more will be the conductivity. That means, the lower the relative density, the lower will be the overall conductivity of the foam. And here the shape of the pores, they also play a very important role. We will see afterward, there have been relations given, and where the, for example, if it is a isotropic foam where all the directions are same, or if it is like a kind of like a laminar foam or a long tube kind of foam, there actually the shape of the foams will have a strong contribution over this lambda S star. The third term of the convection within the cells, again it depends upon the fluid flow, and for that, if the convection is actually playing a big role or not, that actually depends upon one parameter called the Grashof number. So, as you see over here, the Grashof number, if it is more than 1000, then actually convection through the foams play a big role over the conductivity. And this Grashof number is again defined by this relation over here, where this G is actually the gravitational acceleration, the beta is kind of the volume coefficient of expansion of the gas, delta Tc is the temperature difference, and L is actually the cell shape. Now, if we consider that, for example, if we assume that this Grashof number is 1000, because this Grashof number 1000 is the critical value. If the value is more than 1000, then convection will play an important role. If the value is less than 1000, then convection does not play an important role. So, if we then make or render the value of Grashof number equal to 1000 and solve this expression for the known constants, we actually see that we need to have the cell size typically in the range of 10 millimeter, and if the cell size is so large, then only convection to the gas phase will play a big role. But normally, as we have already seen, in most of the cases the foams have very small cells, typically in sub-millimeter range, very often in the micrometer range, and in some modern foams even nanometer range, and that is why the cell size is much lower than when the Grashof number through its influence on the convection will play a role, and that is why the Grashof number plays a very less important role, and we can actually also neglect this sigma C star term, which is the contribution of the convection to the cell walls. Also we can neglect this term. And then the final term which remains is the radiation term, and again for radiation we can use this Stefan-Boltzmann equation, but here again the temperatures of the foams where we typically use them are not that high, and there also this contribution is also not that significant with respect to the first this lambda S star contribution. So, overall there have been, I mean this conductivity of the foams is a very important aspect, and it has been studied extensively for many applications, like especially for many kind of foams, like especially for copper foam or aluminum foam, their application as heat exchanger materials is very important, and for those applications conductivity plays a very important role. And accordingly, people have or researchers have come up with many expressions to actually kind of correlate the conductivity of the foams with the other properties like the properties of the bulk materials, or how much porosity is there, or what is the effect of the shape of the pores and all those things. But and these expressions can be solved, and we can have some relations to predict the conductivity as a function of the pore of the foam structural properties. Apart from that, the conductivity of the foam also depends upon many other factors. As I already mentioned, the cell shape is one very important factor, like if the cells are isotropic, then the conductivity is same along all directions. If the foams are non-isotropic, then the conductivity will be different along different directions, and also it is important that whether the cells are open or closed cell foams. Depending upon that, the conductivity of the foams will also differ. Also, temperature plays a very important role, because in many materials the conductivity depends upon temperature. As we know that for polymers and ceramics especially, as we raise the temperature, the conductivity increases, and as we lower the temperature, the conductivity decreases. So, correspondingly, and also for many gases, as we reduce the temperature, the conductivity also decreases. So, all in all, as we for foams, as we reduce the temperature, the conductivity tends to decrease. Now, another important property which is very important especially for ceramic foams, as I already mentioned, is the thermal shock resistance. What is thermal shock resistance? So, typically you can just simply assume that we have, if a material actually goes to a very fast temperature inversion, that means suppose the material is held at a very high temperature, we can just make a drawing like this. This material is kept at a very high temperature, say T1, and suddenly this is quenched to a room temperature, say T2. So, a very low temperature T2. So, now that means T1 is much higher than T2. So, what is expected when we actually lower, kind of just quench it from a very high point to a very low point, then what is expected? The surrounding of the, because there will be the outer surface of the material, that means if we just draw the outer surface of the material, we will try to lower the temperature, right, because it will try to contract, because the outer surface, when we just imagine that a body is inside the furnace and we take it out and put it in cold water. That means the outer skin of the body will always try to quench very fast, that means it will try to attain the temperature which is attain the dimension for that temperature. So, the outer surface will try to contract, right, that means we have a outer surface which is trying to contract, right, but the inner core of the material, because the core, it will actually have a lower temperature gradient, and it will actually try to, because the temperature of the inner part will remain high. So, that means the lower part will try to resist the contraction, right. So, that means whatever contraction is trying to happen in this part, it is a negative strain, these will be restricted by the inner core, which will try to maintain its dimensions, the higher dimensions at which was there at the high temperature. So, this expansion mismatch, that means the outer section is trying to contract and the inner section is not trying to contract that fast, that will actually put this hatched part or this outer part into a tensile stress, a tensile residual stress. And as we know that ceramic materials especially, they are actually very much susceptible to tensile failure. That means because they are very brittle material, they have a low fracture toughness. That means this high temperature mismatch can actually initiate cracks at the outer surface, and that might actually lead to spallation or some damage of the outer surface, right. Now, this, whether the material will crack or not and how much is the crack sensitivity will depend upon how much is the thermal stress generated. That means, if the thermal stress generating from this thermal shock is more than the failure strength of the material, then the material might undergo failure. If the thermal shock is less, then the material might not undergo failure despite the thermal shock. So, this, And what is the thermal stress? This is again, as I already mentioned, this is the function of the delta T, that means what is the temperature difference over which the thermal shock is being performed. The alpha or the expansion coefficient is again very important, because the more is the alpha, the more will be the dimension difference, and the more will be thermal stress, and the Young's modulus, because alpha delta T is the thermal strain, and if we multiply by the Young's modulus, then it becomes the thermal stress, and the Poisson's ratio nu also plays an important role over here. Now, how is this thermal shock resistance actually defined? The thermal shock resistance is typically defined by this critical temperature delta Tc. That means, this is the temperature difference over which if a material is put into thermal shock, the material will still survive. That means the lowest temperature that will cause cracking in the material because of thermal shock, this temperature difference with the that means this T1 minus T2 or the critical T1 minus T2, which will cause cracking inside the material, is known as the thermal shock, critical thermal shock temperature difference delta Tc. And again, as we see over here, this delta Tc, that means the higher the value of delta Tc, the more is the thermal shock resistance. And as we can expect, this critical or delta Tc is inversely proportional to both E and alpha, as I already mentioned, because the more is the value of alpha and the more is the value of E, the more is the thermal shock susceptibility and the lower will be delta Tc. And the higher the sigma f, the more will be the delta Tc, because in case of ceramic materials, as we know, the higher the sigma s is the flexural strength, the more is the flexural strength, the higher is the fracture toughness too. So, normally that means the higher the fracture toughness, the more will be the delta Tc. So, if this is actually the typical concept of thermal shock damage evolution for bulk materials, and now if we have to convert this or kind of transmit this knowledge to porous materials, what we can simply do, we can actually use the typical expressions for sigma f and E for porous materials, because we already learned that there have been relations typically proposed by Gibson and Ashby, where the sigma f or the modulus of the porous materials, how they actually correlate to the property of the bulk material with or via the relative density. So, this has been done over here, and this way we end up with this expression over here, where this rho star over rho s is the famous term that I have mentioned so many times. It is the relative density. So, we see once again that again the critical temperature of cracking or thermal shock cracking for porous materials, so the porous ceramics, is again dependent upon the relative density rho star over rho s. The lower the value of the rho star over rho s, that means the higher the porosity in the material, the more will be the thermal shock resistance. Why? Because the more amount of pores we have inside the material, the more will be the air, and that will again be able to kind of this more void space will again be able to dissipate whatever thermal stress is being developing, and that will be beneficial to reduce the thermal or increase the thermal shock resistance. That means, ideally, if we want to have a very good thermal shock resistance, we should go for the foams or cellular materials with a very low relative density. But again, we have to remember that this is never a single parameter problem. That means, the low relative density, while better for thermal shock resistance, will also reduce the mechanical properties. So, we have to always find a balance between different properties that we have to consider. Okay. So, that brings us to the conclusion for today's lecture. So, we have seen in this lecture that for porous ceramics, the thermal properties are very important. There are many properties that we can consider, like the melting point, the expansion coefficient, the specific heat, the conductivity and the thermal shock resistance. We learned that both melting point and expansion coefficient, they are not dependent upon the porosity, and their values are actually similar to the bulk material of which the porous body is made of, while both conductivity and the thermal shock resistance, they actually depend upon both the amount of porosity and also the pore shape. Conductivity is a very important parameter, because this controls many applications, and thermal shock resistance is actually very important for especially for porous ceramics, because porous ceramics are brittle materials, and if we put the material to thermal shock, there can be very fast cracking, And that is why we have seen that if we can reduce the if we can reduce the relative density by increasing the porosity in the porous materials or porous ceramics, we can actually increase the thermal shock resistance of those materials. The main reference for this chapter has been taken from the book by Gibson and Ashby, and in the next lecture we will cover about some other properties like the electrical properties, the acoustic properties and the energy absorption behavior of the porous materials. Thank you very much.